My name is Ben Cartwright. I'm going to talk a little bit about some different PocketQube platform concepts that I've been working on over the last couple of years. A couple of brief disclaimers before we start. This talk isn't particularly long, so there will be some time for Q&As afterwards. And the other point is that this is largely to show off some largely kind of phase A designs. Nothing here is really EM, FM hardware. So a lot of this is try to promote discussion and to trying to progress PocketQube platforms into more capable kind of versions of what they are now. I'm here representing two organizations today. One is the Flame Trench, and the other one is my own company, Citadel Space Systems, and we'll talk a bit more about both of those in a minute. Next slide. So, a bit about me. I'm a spacecraft electronics and systems engineer at RAL Space in the UK. I've been there for a little over 3 years now, mostly working on space telescope hardware, so scientific cameras and high reliability instruments. I'm also one of the PocketQube engineers at the Flame Trench, and I will talk a bit more about what Flame Trench is in a second. And then last year, I founded with Julian from the first talk a company called Citadel Space Systems, who largely focus on nanosatellites designed specifically for high reliability science, either in low Earth orbit or deep space. And I have fingers in a few other pies in the space industry as well. So a bit about the Flame Trench. Largely this came about from Twitter while I was still a student. And it was largely from networking with a bunch of British and American students and professionals in the space industry and makers and this kind of thing. And it became a really diverse group of engineers and scientists and students and people who were teaching and content creators and people doing STEM communication. And the Flame Trench really started as a way that we could kind of share what we were working on and show off some of our own personal portfolios and kind of have all that in one place and help each other network and grow in the industry. And that kind of evolved into us working on a couple of flagship projects together, one of which is TFTqube, which is our little PocketQube satellite. A couple of the other ones we have 𝗖cie, which is a robotic observatory, which we're using to do amateur astrophotography and citizen science. And something we've started working on recently is Proxima, which is an open source imager for astronomy, which we're kind of building in tandem with 𝗖cie. We're mostly crowdfunded, so our Patreon is linked there, and as well as our website and social medias. So a bit of the context behind the TFTqube project. One of our members, 𝗖𝗁𝗁 𝗨𝘀, is fairly prominent in the PQ community, and he's a fairly prominent maker as well. And he used to start working on some of these little PocketQube chassis designs, and he had a few versions of these over the last couple of years. And through him and his work with another organization, the Flame Trench had a bit of an opportunity to potentially fly a very cheap PocketQube mission through a CubeSat deployer. And so our plan kind of was, well, we've got a lot of people who are very talented students and makers. Can we build a PocketQube that is not just a really, really basic satellite, but can we do that on the cheap? So we tried to do that, and we had some success, and I'll talk a bit more about where we got to in a minute. So we wanted to do something a bit different from a very, very basic Arduino type computer and a radio module. So the idea I had was, when I was looking at rocket avionics systems in model rockets, a lot of the thrust vector control stuff and more advanced flight computers has really blown up in the rocket space recently. And so I was looking at a design kind of like this on the right here, where you have 5 sections of rigid flex PCB, and you can connect those all up in one piece, and it kind of makes all of your electronic systems much more compact, but you can fit a lot of electronics in a single space. And the idea I had was to fit a battery in the middle here, so you can fit all of this rocket avionics in one really compact space. And well, that kind of applies really well to PocketQubes, actually. And so we came up with a few concepts and really tried to refine this and make it a way so we could really minimize, in particular, the size and weight. Swap is size, weight, and power. Doesn't really help you optimize power much, but it really helps with getting the size and the weight down. And the result is that you can fit a lot more of your PocketQube electronics into one particular volume. So this was kind of our very initial concepts a couple of years back. And here, so you can see inside we have the kind of the basic stack that you get from regular PocketQube electronics. Top mounted antenna. These solar panels don't actually deploy, because it's kind of just exploded for viewing inside. And so you have this key 5-panel rigid flex PCB with all of your solar panels mounted on the outside, and your regular PocketQube systems are on the internal stack. At this point, the key takeaway is that this rigid flex assembly is completely structural. In a lot of other PocketQubes, you'll see they have a base plate, but they have some other kind of mechanical thing at the top. We don't have that. We just have a kind of stack through assembly, and the side panels here do a lot of the structural work in kind of making this all a rigid structure. So this is kind of like the start of the concept, and we sort of evolved this over the next year. So a brief bit about kind of standard PQ hardware. A lot of PocketQubes at the moment are completely implemented in their central stack. All of the OBC, comms, power units, all of your attitude, control, and electronics is all in the central stack. This is from FossilSat-1. Thank you, Julian. So the key thing here is that the PCBs are often still used for the walls because that's a really cheap and easy way of having integrated solar panels, but they only ever actually have PV hardware in. Occasionally you see they have a little bit of sensing stuff on the back maybe, but nothing significant. What we did was we took all of those sort of platform systems and we put as many of those as possible on the inside of the rigid flex kind of shell. So this is the second iteration. We're working on a third at the moment. So the key takeaway for us is that both your comms and your power systems are all on the inside of this rigid flex structure. So comms in particular go on the back of side here where you've got your solar panels mounted, and they also kind of go on this top side on the inside here, and there's a rigid flex connection that keeps them all nice and neat. There's each other solar panel has its power mounted on the back as well. So things like your protection diodes, your power optimization circuitry and stuff like that, maximum power point tracking, all of that is on the internal side of this solar panel. And actually the only thing we had on the internal stack was our OBC setup, and that actually gave us a lot more space to have a particularly complex onboard computer with external memory, external MRAM, to try to heighten the reliability of the system. The nice thing about this is on the inside you can sandwich your battery in between some of your radio, your comms tech, and your OBC, and that helps keep the battery warm naturally. And what we do is we have SAMTEP connectors between the inside of the top side of the PocketQube and this internal PCB here, and that connects the two systems up. So we have like quite a dense, low profile connector to join those two up. You can see the results of this, of moving all of these stack systems onto the actual shell itself, is that you end up with a particularly large payload area in comparison to most of a 1P PocketQubes. So if you go back to this is kind of all your platform and maybe one board for your comms payload. Here you have pretty much 2/3 of the internal volume exclusively for payload electronics and hardware. So this is kind of one of the key benefits of a system like this. The other thing we built in was GPS. So we had an extra board mounted on the bottom of the base plate here with your GPS antenna. And if I go to the next slide, you can kind of see how we connected that up. So if you think about the internal PCB here, we have a high density connector connecting the rigid flex shell to the internal PCB. That kind of doesn't work if you want to connect anything to this extra PCB on the bottom. So we built up this flexible harnessing, which is actually used quite a lot in industry for particularly dense instruments and things like that. So we're making use of extra SAMTEC rigid flex connectors to link all that up, and it makes this kind of really flexible as to what you can mount on different PCBs or different parts on the bottom of the base plate. You can kind of chop and change depending on what your payload is. You don't have to have solar panels on this side, for instance. You can have a cutaway and have an observation payload and that kind of thing. It's very, very flexible. So what we're planning on doing with this is opening it up to students, either in Britain or in the US, because that's mostly where the flame trench tends to work. And we will open up a tender for students to fly an experiment on TFTqube, and we will help them with engineering support and building it up. And the idea is to kind of turn this into a sort of STEM communication and outreach project. It's only possible with the continued crowdfunding that we've been very lucky to have for the last 2 years. But likely with the amount of work it is taking to kind of get a more difficult concept like this to fruition, we were looking to start to open this up to the community, and we hopefully have some more details about what that looks like soon. So yeah, so that's where we are with that. A bit of the progress here. So we're working very heavily on the structural models because this is quite a unique assembly from a lot of what else I've seen and people working on. So this is the second iteration. We're working on a third at the moment to try to simplify some of this. I can see I've got it here. If you can see what I've got in my hand. So here's our structural model. You can see it's very, very small. I apologize. Inside, all of this volume in here is available for payload. And the rest of it is platform systems. But because of all that is mounted on the rigid flex, it's very, very compact. So we're prototyping GPS and radio in the US at the moment. We're using OpenLST by Planet Labs, although one of the parts is now end of life, so we're having to kind of rebuild it a bit, which is a bit annoying. But once it has been rebuilt, we will re-open source it, and everyone will have an updated, more current version of OpenLST. One of the cons of this kind of setup is that this 5-piece rigid flex assembly is absolutely not cheap. You're looking at a couple of £1,000 for a production run potentially, compared to well, for a 4-layer regular PCB. It's less than £100 depending on what your reliability is. So there's a very, very stark contrast between kind of hobbyist pocket cubes and the sort of price that this is going to end up at. So something else we're looking at is kind of how do we achieve this result without this big rigid flex assembly? And we're looking at things like board to flex connectors, and still trying to maintain the structural aspect of this while also using board to flex connectors is kind of difficult. So we're really trying to find out how we can simplify this but keep the benefits of that really compact system. So taking some of the lessons from this and how do you fit really highly optimized PocketQube hardware into a very, very small volume. This is something else we're working on with my company, Citadel Space Systems. So it's kind of asking the question, where are PocketQubes useful and where will they be useful? And the idea is that we don't think they're only useful for amateur space, and we don't think that they're only useful in low Earth orbit. We think that amateur space is applicable beyond low Earth orbit, which has previously not really been done. And we also think pocket cubes are applicable both in general for science or for private industry, in exotic destinations like around the moon or planetary destinations. So Citadel Space Systems is really here to try to create inexpensive yet reliable nanosatellite platforms for deep space. That is obviously applicable to low Earth orbit as well when you've got really long flight times. Obviously, most CubeSats right now are around 6 months to a year kind of lifetime. We're sort of targeting 3 to 5 years and up, which is applicable both to obviously low Earth orbit and deep space. So this is kind of our flagship capability that we're working towards, is a 12 to 16 CubeSat for deep space flight. And kind of having this capability leads to being able to fly pocket cubes to very unique destinations. So this is the pocket cube that we're working on. This is called Squire. This is the 3P version of it. There'll be a 1.5P and a 3P version. And we're using the kind of the lessons learned from TFTqube with this flexible harnessing and rigid flex stack-up design to try to maximize the internal volume here and maximize the amount of systems that we can fit. And this is really, really useful and kind of necessary for deep space because obviously you don't have a magnetic field. So you've got to be able to deal with things like attitude control, which is all well and good with reaction wheels, but you have to have a way of detorquing them. And so being able to fit in things like attitude controlling electric thrusting, propulsion systems, that kind of thing, it's difficult to do unless you're really optimizing all of the volume inside. And so the lessons learned from TFTqube are being very much applied to this platform design here. This has 20 watts at Earth, which translates to about 8.5 watts at Mars, which we figure is more than enough to be able to do useful things. And the kind of the crux of this is that we're looking at up to 9 of this platform being deliverable by a 16U CubeSat. And a 16U CubeSat isn't really that expensive if it's ride sharing somewhere in comparison. I say that expensive. So really, this CubeSat delivering PocketQube concept we think is quite a unique but inexpensive way of delivering PocketQubes to destinations that they haven't been able to go to before. And so kind of in that vein, this is another concept we've briefly been looking at, and it's a bit different to where PocketQubes have gone yet. This is a 6P PocketQube that we've been looking at. This sort of larger design is mostly made possible by the fact that we've developed a slightly different standard. So if you look at what we've got here, there's a base plate on the bottom. What we've actually got with our standard is a base plate on the top as well. And that allows us to expand this and kind of maximize our internal volume and maximize the amount of space we have for both platform systems and instrumentation. So this one has about 30 watts at Earth, 12.5 at Mars. And this is kind of, both the 3P and a potential 6P are kind of instrumental for us envisaging PQs as platforms, both for science around other targets like near-Earth objects or planetary targets and things like that, as opposed to just AMSAT things around low Earth orbit. So we want to see this kind of next generation of PocketQube really take off and show that these kind of really, really small satellite platforms can actually really be useful. Special mention to Applied Ion Systems, who we're collaborating with to develop electrospray propulsion. We've been working to implement these in both PocketQube form and CubeSat form. And so we'll have some more information with that over the next few months with any luck. So the last bit to round off a bit about this standard. So really what we're doing is taking the lessons learned from the ALBA, Delft, and GAL standard and trying to both apply it for deep space use and fix a couple of issues with it. So the ALBA standard has a single base plate mounted in rails. We have essentially the same thing, except we have an extra base plate on top. And the idea is that this eliminates the rotation that was seen in some recent PocketQube launches. So your PocketQubes will deploy A, slowly, and B, stably. So very high degree of stability and a very, very small amount of delta V from the actual deployment, which makes it very, very useful for PocketQube deployments around things like near-Earth objects, where you're doing very, very fine adjustments to get into a certain orbit around that object. So both of those kind of characteristics make this very, very useful for deep space. The deployment that we're working on, the longbow deployer, is mostly applicable for being mounted inside CubeSats or other small sats. It's not really designed for mounting on large launch platforms. So it's kind of unique in the market as it stands. And so we have an example here where this is what we call a cluster config, where it's actually kind of tighter than the ALBA setup. But this is what the deployment looks like when it's a 3x3 3P PocketQube deployer, so 9 PocketQubes on one CubeSat. For small amount of PocketQubes, this gets bigger, and the idea is eventually this becomes able to supply a larger external deployment volume than the ALBA one. So things like the larger solar panels that we saw, or bigger antennae, or things like that becomes a lot more feasible with a platform that can do this. The other key point is that this is completely back compatible with the open standard. This base plate dimension is exactly the same as ALBA. So a Squire CubeSat can fly on an ALBA pod. A unicorn or anything designed for an ALBA pod can fly on this to deep space destinations. So it's very, very flexible. We're not looking to kick other people out of the market. We're not looking to make PocketQubes difficult to fly. We're very much in the business of trying to open up more destinations for people building interesting small sats. And the other key point is that we're pushing this draft online very shortly. So thank you very much. These are all my links.